Hello everyone, welcome for today's discussion. So what we have for you today is one of the most important topics in linear analysis. This is Reimann Integral. I believe that you have encountered integration in your class. So how did your teacher introduce this integration topic in your class?
Sir, our teacher introduced integration using rectangles and then summing all the areas of the rectangles, which will serve as the approximated value for the integral of f.
The approach that your teacher used was the same as what Reimann did. The approach is known as Reimann Integral. Reimann Integral allows us to integrate a continuous function as well as those not too badly discontinuous function. However, Reimann Integral has its limitation. There are functions that Reimann Integral fails to integrate. That's why there exists another type of integrals. One of these is Lebesgue integral. The geometrical interpretation of the integral of a function is like finding the area under the graph of y equals f of x. Consider this function f a mapping from the closed interval ab to r, and assuming that f is continuous and positive for simplicity. So the integral of f is just this region, the area under the graph of our function, and between, because we have specified that our domain is this closed interval. So the area is just this one. If we can somehow determine the area of this region, we call this number the definite integral of f from a to b. This time, we will try what Reimann did in finding the integral of a function. What Reimann did is he used the rectangles. Because as observed, the area of the rectangle is easy to calculate. In short, Reimann tried to approximate the area of the region by using suitable rectangles, getting the area, and then summing those area of rectangles. Consider this illustration. First is, we have only one rectangle, and then we split this one into two. Splitting again, we have 4 rectangles, and we have 6 rectangles. Based on the illustration, what can you observe as we increase the number of rectangles?
Sir, taking narrower and narrower rectangles, the resulting approximation converges to the integral of the function.
Yes. Now we make this procedure precise. As we can observe, the widths of the rectangles are determined by splitting the interval AB into smaller segments. So this time, we will use the notion of partition. Consider a closed interval AB. By a partition AB, we mean any finite set, let's say P, that contains these points from the closed interval AB, such that A is equal to x sub 0, which is less than or equal to x sub 1, and this is less than or equal to x sub 2, and this one is less than, and so on, less than to x sub n, where x sub n is equal to b. Now assume a bounded function which is defined in a closed interval AB, which is split into n segments that determine the sides of the approximating rectangles.